Let's continue with this series on the different kinds of controllers. And today we will see the PI control as well as the PID controller. We have an example on the screen right now. As you see, this is the plant that we have in here, and it's a simple feedback loop on a variable that comes out of the plant in here, and then you have the reference point. as, as we know in here, this is going to be our input in here, yeah, and of course this is our output here, yeah. So what happens in here is that we feedback this, and we create, this is the controller. It has a proportional control in here, and then it has a additionally integral control. So let's see what happens when we put this in together with a first order system. Why do we say first order? Because the power of the denominator of the transfer function of this plant, now that we know that this block is your plant or your system, see, is first order. So these are the, if you put this kind of system together, this is what you should expect. So steady, stable for positive values of Kp, or the proportional control, and the integral control. So a stable system. 2, response to a step input, which would be a step input over here of the kind like this, where we have a step just like that. We will see that you obtain the omega steady state equal to 1. So very stable control. Offset error is 0. Response to unit step also has 0 error at steady state. And in this case, we have put the damping ratio in terms of the two constants of the Kp as well as the Ki. This allows to be selected without fixing the value of the dominant time constant. So here's an example, for an underdamped system, and then you can pick those to create a specific damping ratio. The proportional control will be picked to determine that, and then Ki would be used to set the damping ratio. So, what it's saying is that you can accommodate those values depending on what you would like. What you're seeing here on the overall transfer function, what we have done here is combine this block plus the plant and obtain an overall transfer function, which is what you see here. All right, so that's how you build a PI controller. If you have a system whose plant now is a little different, so I'm gonna write in here again, this is the plant, but because of this and this is second order. All right, so if you build this type of control, you have Kp plus K sub I. This would be the um, you'll have this would be the transfer function. The steady state performance is good if the proportional control and the integral control uh, the if this ratio is bigger than 0 for second order system. Okay, so for a small c, the damping constant in this case, Kp must be large in order to satisfy this condition. And one conclusion, this kind of not so easy to implement this. Also, if a Kp is larger than 0, the time constant may not be satisfactory. The analysis of third order equation done using the root locus, excuse me, there's an error here. Root locus method is we will see that on a next lecture video. Okay, let's take an example in here on what we're doing and look at the pneumatic liquid level control system. And I would like to take a look at this example because at first, the first impression that it gives you is that it is a complex control system, while in reality it's not. Let's just take a look in here. This is a reservoir, yeah, just could be a tank, and then you have this is a tube that has been put in there to measure to have a sense of where see, this is a tube is continuous here. Okay. To measure, to get some feedback on where the level is. So the idea is to control where the fuel is. Okay? So H, of course, would be the level, and X is going to be where how deep it is. Now, as you can understand that the pressure at this point depends on how deep this is in there, yeah. So on what the pressure is in here is going to depend on how much fluid you have. It's hydrostatic pressure, right? Okay, so the idea is that if this is full, with air in here, it's going to feed back over here. So it goes like this and then turns like this, and then you will have a pressure coming this way. So these are some bellows. Those bellows are like some bags, you may say, that if you put a bit of air, it's going to expand. So what happens when there's liquid here? This bellow will inflate and would press this lever here. Yeah, it would produce a moment about like that, right? A rotational moment. Let me see if we can do something here to right here. Let's try this. It's a little easier to see if we're doing call. So it will produce a moment like this if there is pressure over here, right? And this will rotate. So when it rotates, you see, and this thing goes up. By doing that, what happens here? Opens this valve, yeah. And when there is a the okay, the need. This is the point set pressure. So this is a pressure source right here. Source. So you open this and set the level. Yeah. Actually, not pressure source. It's level set condition. So here we have this. And then here's where we control how much the pressure should be over here. Is to calibrate the system. So depending on you see if the pressure here, of course this I'm gonna call it pressure from feedback. I'm gonna call it pressure from the set point. So if the pressure from feedback is bigger than the pressure for set point, this opens and then the fluid goes in. But if the pressure is not enough, this thing is I would say if the pressure not enough, if the pressure here is bigger than the other side, this is going to be down and it's going to be closed. All right. So I think that is depending on what you measure here and how you set up on which side the opening condition will happen. Um, when there's not much water here, then obviously the pressure on this side is going to be bigger, and then this valve is to open or close depending on what we're doing. So um, so this is the control valve, and this would be the liquid supply. So we could interpret it that if it is going down, well, let's see clearly how it goes. It's going down, you could say it's closing, right? So that is if it's going up is opening. But all of this works depending on how this pressure are set up for where the pressure on here is low, then this will produce a open condition. When gets a little higher here, and then it is equal to this, then it'll be closed or it's bigger. But okay, so in here you have the system differential equation, which is the A times dH dt. This is the volume per time. Is Q, which is the supply minus the square root of RT. So here's the idea would be what the value of X is, what the value of W is, and depending on that, the controller acts. So if you have in here the on a linearization, you may say of the system, you could take the derivative of the flow, and then when we're talking about the beam, we are referring to this beam. Depending on where the beam is, that's how the controller works. Okay, so in here we know how to, well, we have linearized the system and have this you following the derivative with respect to y, so and x. So the motion of the beam depends on the set point pressure, and feedback pressure will in turn depend on h and r. The idea is, how do you build a control system of this? Because this, in a way, this is a first order system, right? This first order. Yeah, we have in here like that. And you have these two, the controller always remember is this thing in here. Okay. This is the, this block converts the signal that comes from the, this is the physical measure from X, and compares, in this case is comparing pressures, okay? And that's how the control system works. Now, let's switch gears a little bit. We are going to combine then all three of these now. So what you have is a PID controller. So this would be proportional control, which would be represented here. It has integral control, which is here, and also has derivative control. Okay. For example, you have an example, this position control. It says that only with PI is not satisfactory because if C is small, oscillations were generated. So you don't want a system that oscillates and you only have integral control. So you need to enter this derivative control, which is like damping on the system, and you enter it here. This obviously, if you have S times S, this is S squared. This is like I S squared plus C times S, like that. So this is a second order system, although one of the roots is at 0. Yeah. If you combine this plant plus the control, you will obtain this transfer function. This would be the transfer function for the output here in relationship to this input. Yeah. So you have two transfer functions here. The output with respect to the input, or you have the output with respect to also the input, which is the disturbance. So you could study the reaction of this with respect to the input, which is here on the left, to the set point, or with respect to the disturbance. Remember, always transfer function is a relationship between one output and one input. So this is let's just do a little summary here. Any combination of these controllers can be made depending upon what the system requirements are. PI controller stands for proportional and integral control. PD control, proportional and derivative control. And PID is for the combination of all of them. In this case, you can see the control law has contributions of the proportional, integral, and derivative control. K's are the gains. So depending upon the action that is required, the gains are adjusted to achieve the required control action. Okay, so let's just go back, and we stop the summary now.